creepy screen, of course. All right, so we're having a quiz on estimate statements, everyone's favorite, right? No sarcasm. Broad enough if you wanted to show via a picture, for instance, what the model is saying. You would need more predicted outcomes, so that's one use of an estimate statement. Simple slopes out of an interaction is another. So for instance, if I have an effect of age by group and I find a significant interaction, I would want to know potentially what the effect of age is in each group so that I can talk about how they differ from each other. Estimate statement. What you'll get by default is only for the reference group. You would get an effective age for group 0, but not for the other ones. If you had more than 2 groups, you would get how group 0 compares to each of the other groups, but you wouldn't get what it is in each group. So simple effects of interactions, estimate statements can get you. Pairwise differences between groups, broadly construed, either in slopes or intercepts you can get. So this is a skill that helps you, I'm not going to say decompose, I will say understand, probe if you will, although I still hate that word, what linear models are telling you and how they address your research questions. And understanding how the model is parameterized and thus what the effects mean can be tricky. And the example that we have today shows an example where you may have an effective group somewhere on the output that has one p-value, and you keep scanning down and the effective group has another p-value. And you're like, which one should I look at? What do these mean? Why do they differ? So I want you to understand those issues. So with that preamble, let's take a look at how this went. So I have my answers up here. Number 1, writing out a predicted value equation for somebody who has this set of values on the covariates. So to make it easy, I'm assuming that these are the centered values, so I didn't tell you that these are such that you have to do subtraction and whatnot. So we just fill in the values as they are. So we have the effect of F for somebody with a 2, the effect of G for somebody with a 3, the effect of H for somebody with a 4, the effect of I for somebody with a 5, and then the 2 interaction terms that would involve multiplying the relevant values together. Okay, did that part go okay? Okay, that's something you probably have a lot of practice with. Something that you have less practice with is making SAS do it for you. The estimate statement that accomplishes this calculation is right here. Intercept 1 means I need 1 beta 0. F2 refers to 2 beta 1s. G3 refers to 3 beta 2s, and so on. So the letters are the names of the variables, actually refers to their beta weights, their fixed effects that SAS has estimated and has in its memory. You let how many of them you need as a function of what the values of the predictors are that you're trying to calculate an expected outcome for. So stare at that, compare it to what you have. Questions on number 1? All right, let's keep going then. So we have a couple of two-way interactions in this example model. Let me get the F and G and F and H. So in terms of labels here, if I'm staring at my equation, this effect of F right here, this is conditional or simple. This is specifically when its interacting predictors are at 0, which means when G is 0 and when H is at 0. Likewise, this effect of G, because it's embedded in an F by G interaction, is specific to when F is 0, so it's also simple or conditional. H is embedded in an F by H interaction, so it's specific to when F is 0. But what about I? I doesn't have any interaction terms with it, so it's marginal. This is the effect of I for everybody. So with that in mind, if I ask you, how do I get the predicted G slope? I pull the relevant terms out of the equation, which means everything that has G in it. Everything that has G in it, no more, no less. So at a minimum, the G slope is given by beta 2. If I want to know what it is for someone with f of 2, then I need the interaction between f and g, and I need to give it a value of 2 for the moderation by f. So the estimate statement then would look like this. G1, meaning I need 1 beta 1, and I need 2 f by g interactions. Any of that you want to hear again or hear differently? Clear as mud? That's a Midwestern expression, right? Or maybe I'm just dating myself. Oh well. Likewise, the f slope. In this model, f interacts with two other predictors. It interacts with g and it interacts with h. So I need the main effect of f, which is what it would be when g and h are 0, plus how the main effect of h depends on f, or excuse me, how the main effect of f depends on g, and how the main effect of f depends on h. And so I filled in the values here for the moderation g and f, or g and h, I can't even read, of 3 and 4 respectively. So the estimate statement would look like that. And then last but not least, the I slope. I was trying to trick you here. Did anybody fall for it? Yeah. I'm like, I for this one and that one and this one. The I doesn't interact with those. So it's just the effect of I for everyone. I could come up with an infinite list of for f of this and g of this and h of this because I doesn't interact with them. I is unconditional, it's marginal. So this is what it is. It's beta 4 for everyone, which means just that slope all by itself. Did that go better than last time? Do you feel like your notes helped you? Even if just psychologically, it was comforting to have them? Yeah, okay, good, fine. The reality is that there's never going to be a time in your life when you are asked to dump your brain without any resources around you, right? You're always going to be writing with notes, except maybe comprehensive exams. Does anyone have to do that? Sit in a room and dump your brain? A couple programs still do that. I really hate that because that is not a skill that you need in your life. So, lest I be a hypocrite, have some notes. If it makes you feel better, have some notes. So I will take a look and see how those went. You're getting lots of practice with estimate statements as well in homework. So homework 6 is in progress, due Friday. Homework 7 is up, and that is due the Friday after Thanksgiving. So you can ignore it for an entire week and then come back after Thanksgiving break and get it done. It's a shorter one, as you will see. I'll click on it here. It's, you already know everything you need to know to do it. It's just practice with interaction. So a few computational questions from a main effects model, a few from a model that has two-way interactions, and then some from a model that has three-way interaction. So not too bad relative to the piecewise homework, which is giving everyone fits right now. So while we're on the topic of homework, would anyone like to ask questions on our current homework 6 here? Piecewise models. Charlie.
Am I correct to assume that if we're getting a convergence problem, that
Yes. Make sure that you're what? I'm sorry?
it only happens for the saturated part?
Make sure you're not doing an unstructured variance. I think I just asked for random intercept.
It's -1.
It's -1?
Unstructured.
Oh, yeah, no, don't do unstructured with this data set. I think I just asked for saturated means, in this case with the random intercept. So this is a case in which, in theory, it would be possible, but it's too much to estimate the 13 by 13. Make sure you're using ML for everything. That's the other thing I've been troubleshooting with folks. Any other questions or problems? Yeah.
Just for curiosity, can I output everyone random effect?
Yes, you can. you would add the word solution after the slash on the random line, and you better go make some popcorn and wait because it may take a while. All right, Aaron, did you have a question?
On the topic of estimate statements,
Yes.
I mean, it might be a long question, I'm not sure, but I guess I'm just having trouble writing an estimate statement for the occasion that actually, like, it's giving me something.
It's giving you something, which is a start. That means you've requested a quantity that is possible, but it's not turning green, and so it's not the right quantity?
Yeah.
Okay, which part are you on?
The last part.
The last part. Section 4. All right. Model predicted. Is that where you're at? Model predicted mean stress at each occasion? No? Okay. Which one are you on?
Like, are we not writing estimate statements for linear change?
Some of them, yeah.
Okay,
Okay. So like 44 and 45, enter the estimate for the linear rate of change at occasion 7 and the linear rate at occasion 1.
Yeah.
Okay. Well, one of those is easier than the other. Occasion 7 has a special significance in this model. It's the intercept, right? So it's where time 0 is. That means that the estimates that show up by default are going to be for occasion 7 in some cases. So that one's easier. For occasion 1, you do need an estimate statement. I would recommend revisiting how you get instantaneous linear slopes given a quadratic rate of change from the first part of example 6, where we'd had linears and quadratics. But keep in mind that time is backwards. You're going negative in time. So make sure that your sign is correct. It's twice the quadratic is how the linear slope changes per unit time. So you'd fill in the value of time you want it for times 2. Other questions? I've entertained several questions over email, so if you're thinking you're the only one who hasn't got it all done yet, I will tell you you're not. This is one of my prouder homeworks of ass-kicking, I have to say. I'm very proud of this. Yes?
So the questions 9 through 16, coded value of the phase slope predictor at the occasion.
Mm-hmm.
I'm just wondering what specifically you're looking for there. They went over something like this online.
Yeah, I don't know how else to say it, but what I'm looking for is just to make sure that your slopes are coded correctly. I want you to enter like these numbers. So what did you put for occasion 1 for this slope? What did you put for occasion 5 for this slope? That's what I'm going for. The coded values. So not fixed effects from the model, just checking that your slopes are set up correctly.
If I entered that, it's saying it's not right.
Then maybe your slopes aren't right. So we did an example last time that is similar in structure to what your assignment looks like, where we had the intercept was 3 in this one, and we had a slope that happened before 3, a slope that happened from 3 to 4 and then shut off, and then a slope that picked up from 4 to 9. Okay, so that the pattern is the same. All right. Other questions? Can I show you guys something real quick to make you feel better maybe? Because I think some of you might hate me right now. Did you know that I don't know everything? Did you know that? Even about statistics? So my dear husband sent me this article because it's relevant to something that I'm working on, which is how to estimate a certain type of IRT model in M+. And I started reading it while you guys were doing your quiz. And I came across, as motivation for why this article was needed, they talked about what is known or not known in the literature. And I want to cue you into this sentence. And several graduate course lecture notes located online indicated uncertainty that M+ can estimate these models. See, for example, me. And him. So I click on it, And yeah, there is a lecture from my old 948 at Nebraska where I did things in NL mixed because I didn't know how to do them in M+. So it could be worse, right? You could be sitting here like feeling like you're you don't understand something or that everyone gets it but you, but at least it's not in print. That you don't know what you're talking about, all right? So it could be worse. Although they said it in the nicest way possible. I expressed uncertainty that this could be estimated. I'm pretty sure what it said is, I don't know how to do this or it can't be done. I'm not sure which it is. That's probably what I said. So, life is one big learning curve, right? No. Nope. Nope, they just, and that's not the first paper. Actually, there's one paper that was published that literally the entire point of the paper was how I said SPSS couldn't do something and they found a way to do it. And that was the entire paper. Seriously. It, like, the title of it was "Nuh-uh," and I got to review it. I don't know these people, but like literally it was like a rejoinder to something I wrote like 6 years ago. I was like, you know what, you win. SPSS can do it, my bad. I hope you feel better about yourself now. So, I digress. We have more on interactions to do today with grouping variables. So this is where it starts to get even more fun. In this case, the simple effects that we would be asking for are logically constrained by what groups are in the analysis. So it's not a question of selecting arbitrary values of what high and low are to get simple slopes, but also just to try and find out which group differences are present and which aren't. And thus, how do we describe interactions involving groups? So this is lecture 2C I'm pulling up here, if you'd like to join me. So the first part of this is just review. We went over this back at the beginning of the semester. I'm going to go ahead and assume that you didn't memorize everything I said 2 months ago and that we want to hear it again. Is that a fair assumption? Yeah. So when you're dealing with grouping variables, or what I call categorical variables, you have two choices into how you tell the software to handle them. Number one is you do it yourself. You do not let the software do anything. You create contrasts that are specific to what you want to know, such as by dummy codes, and you enter those dummy codes yourself, and only you know what they mean. This is useful for teaching purposes, I think, because it corresponds to a linear model representation more directly. It can also be easier to set custom contrasts for instances where you want to compare maybe like one group to the mean of two groups or something like that that's a little bit atypical. It also can be a lot more code in the long run. So whenever you have a situation in which you have more than one grouping variable, and for instance you want to see interactions between grouping variables, it can often be easier to let the program create the contrasts for you. And so that's what you're doing when you put variables on the class statement in SAS, the by statement in SPSS, IDOT in Stata, I think in R it's called a factor maybe. There is no way to do this in M+ though. That I know of. Now someone's going to write a paper and be like, nuh-uh. As far as I know, M+ does not have grouping variables. So take that, universe, see if I'm wrong. I would love it if they did, so I would like to be wrong in this case. So this is more convenient if you have a lot of grouping variables and experimental designs where you do specifically want to look at the combination of cells and whatnot. It can be inconvenient for other reasons though, as we'll see in our example. So these are the two options that you have. I want to teach you how to do it either way so that you have maximum flexibility with how you specify your models. So the first way, you do it yourself so that you know what everything means. For the control freaks, this is the way to go. So for instance, if I have a treatment group variable that has 4 levels, I have a control and then 3 flavors of treatment, I could create 3 dummy codes that contrast the reference group control to each other treatment. I would put them each in the model So this is what I mean when I say that the manual coding represents, it goes more with the linear model representation. Even though you're thinking of group as one predictor, when you enter it into a model, it's the number of levels minus 1 parameters for every term. So to enter group, I have 3 fixed effects. 3 fixed effects to distinguish the 4 groups. The model then tells me what the predicted mean is in each group. It's the intercept all by itself for the control group. It's the intercept plus beta 1 for the first one, plus beta 2 for the second, or plus beta 3. So what that means then is that by default, you are only going to get 3 of the possible 6 group differences. You get control versus each treatment. What you don't get is each treatment relative to each other. But it's there. If the model understands what the mean of each treatment group should be, it also understands what its differences should be. So the first 3 differences then are given directly by the betas. This is control versus each. If I take what the model says the mean should be for each group, to find the difference, I just subtract it. So treatment group 1 versus 2, where I have 2 minus 1. If I just do the math here, the beta zeros cancel, and I end up with beta 2 minus beta 1. So this is an instance in which the model knows what T1 versus T2 should be. It just doesn't give it to you. But you can ask for it via estimate statements and LS mean statements. Estimate statements in this case because these variables are being treated as continuous. Likewise, it understands what all the other ones are as differences in the estimated betas. So to do this in SAS, here is all the code you'd have to write. It group manually via these contrasts, D1, D2, D3. The first line right here, after model, this contrast, that's what is known in ANOVA language as your omnibus main effect. It's a 3 degree of freedom test of whether there's any group differences. And to do it, you list all 3 contrasts separated by commas for each one so that it gets the right degree of freedom. And it's testing all group differences simultaneously via these 3 contrasts. I can then ask for what the predicted group means are for each combination. And then I have the dummy codes that directly provide the differences. So I have these ones, the first 3, control versus each other, already as model parameters. It's the last 3 that I have to get. So I write out everything so that you can see the patterns, but it's really just these last 3 lines that you would need. To get the difference between the betas, you put a -1 on one and you put a +1 on the other. Doesn't matter which is which. I usually write it out as one versus the other, and I give the first one a -1 and the second one a 1, but you'll always know who's higher because you've already asked for the means. So if you switch the -1s and 1s, the direction of the difference switches, but the significance would be the same. So it's just a choice that you get to make. Doesn't matter. Okay, with me so far? All right, now, what if I have an interaction term? So let's say that I have group with age. I want to know if my treatment is equally effective for people of different ages. That's something I might want to know. So to ask that question, does age moderate treatment effects? I am adding 3 interaction terms, 1 with each of the dummy codes. So I now have an omnibus main effective group, and I have an omnibus interaction with age. Each of these is a 3 degree of freedom thing. What's the other terminology that you learned to describe this idea of testing multiple things at once? Multivariate wald test, that's what this is. The terms that you learned in ANOVA omnibus, it's a special case of this more general idea of testing multiple fixed effects at the same time. So there's a whole lot of information that you might want to know that isn't going to come out of the model. For instance, does age matter? Well, I can't just answer that question because it has to be a more nuanced answer. For which group does age matter? Any of them? All of them? Some of them? What I get by default is the age slope for the 0 group, which is control. That's what the main effective age that I get by default is going to tell me. I'm also going to get the difference in the age slope between control and treatment, between control and treatment 2 and control and treatment 3. But that isn't going to tell me whether or not there is an age slope for each group. I still wouldn't know that. So here, in the first 4 sets of estimate statements, I am asking for the missing pieces of information. Age slope for control, age 1, because that's the age slope is the thing I'm asking for, and if it's for the control group, that's when all these other dummy codes are 0. If it's for the treatment 1 group, I start with the main effective age for control, and I add to it how the age slope differs in treatment 1. So age as beta 4 plus beta 5. That gets me to what the age slope is in. Likewise, if I start with the age slope and add the second dummy code, that gets me to the age slope in the second treatment, and then the age slope in the third treatment. So now I can answer the question, does age matter in the control group? Does age matter in each of the treatment groups? That's something I would want to report, most likely. Then the next layer of inquiry, does age matter more in some groups than others? Well, there are 6 differences between the age slopes in the same way that there were 6 possible differences in the intercept before we had age in the model. The model output is going to give me 3 out of the 6. The interaction terms of the dummy codes with age will give me the difference between control and each other treatment. To know if the age slope differs within my treatments, then I do the same combination of -1, 1 with the relevant dummy code. So -1 here versus 1 here gives me 1 versus 2, 2 versus 3, and 2 versus 3, and then 1 versus 3. So if I found, for instance, a significant omnibus interaction that somehow age interacted with group, it's like, now what? How do I talk about that? These are the things that come next. More specifically, age only mattered in the control group. It did not matter in the treatment group. Things like that help you explain what the pattern of the interaction is. Something that people do that is ultimately misguided in this case is doing t-tests. They start doing separate analyses where they do one group at a time. You can't do that unless, let me put it this way, unless your model has different residual variances by group. This model has the same residual variance groups, and so if you do t-tests to break the groups apart, you're creating a different residual variance. It's not the same. So it's far better to ask for whatever contrast you want within the overall model, because then they're going to be tested with the right standard error based on whatever variance structure you have. When you split the groups and do separate analyses, you're changing the variance structure, so it's no longer the same model. Okay. How are we doing? We're doing? In this case, I know there's not, because there's no statements on here that refer to variance. There's no random and there's no repeated. If you omit repeated, the default repeated is VC, which means equal variance across the board with no covariance. If I had wanted to test for different variances by group, you could do that. That is a repeated statement after the slash that has group equals and then some grouping variable. And it's a likelihood ratio test as to whether the model fits better if you give each group its own variance or not. In this setup, it very well may be the case that you need different variances by group. If people are more homogeneous in the control group, then we need to allow a different amount of variability as a function of treatment versus control. That's a likelihood ratio test waiting to happen. That's something that we'll do more with next semester if you stay with us. Speaking of which, several of the clinical child folks have told me they can't come next semester because you have already too many classes to take and they only pay for 9 hours. Here's what I want you to do if you can. Come anyway, for free. I don't want you paying like actual money for this, but just feel free to come. Come hang out with us. Auditors are always welcome, right? They're not paying. And I'm not making them like, you know, hand out paper or do grading or anything as, you know, slave labor. Just feel free to come. All right. So this is one way of doing business. The other way of doing business is to let SAS do the coding for you. Advantageous in some respects, but not others. When you let SAS do the coding, it changes who the reference group is. It's the highest group. There is an option in SAS that I thought would work to change it, but it only changes it in parts of the code, and so it actually makes it way more confusing, so I would not recommend that. You'll end up getting your multivariate wald test for your omnibus test by default rather than having to ask for them. And it's easier to use LS means to get predicted group means as well as predicted group mean differences. Let's see, Stata, the default is different. It's the lowest or first group. SPSS, it's also the last group. So just keep that in mind. It may or may not be the right reference group for you, but if you know how to do these estimate statements, then it doesn't matter which reference group it wants because you can ask for whichever contrast you want instead. So you saw this before, but just to reiterate, treat group is now on the model line and it's on the class statement. That means it is going to create the 3 contrasts that differentiate the 4 groups. That additional line below it is LS means, which you've seen before, which is how you get what the model says the predicted mean is for each group. Diff equals all. Can you guess what that does? Can you guess? Stephanie, can you guess? It tells you all the differences. You don't even have to know how many there are. Those 8 characters and it figures it out. It's beautiful. So by using the class statement and adding this one line, it gives you everything that's on the rest of the slide. All that stuff comes out for you without you having to ask for it. I've written it here so that you can see what the differences look like if you do have to ask for something via an estimate statement when you have a grouping variable that's treated as a categorical variable by SAS. The biggest difference is that every time you reference this treatment group variable in the code, you have to list as many values behind it as there are unique groups. And it is in the order of the data. So it goes numeric or alphabetic. If you're using value labels, like you use proc format and give it formats, it's alphabetic. So you have to know which group is which ahead of time for this to make any sense, but most of the time you will know that already. So to get the control group mean, it's the intercept, and I have to indicate for which group I want the intercept. There is no default value for treatment group that it has if you don't write it. You have to always indicate for which group you want something. If I want to know the difference between groups, like control versus treatment 1, if I take one of these lines and subtract the other, the intercepts cancel, and one of these ones turns into a -1. And that's the logic by which this first statement works. So to get differences between groups, one of them is a minus, one of them is a plus. They have to sum to 0. Any group that is coded 0 is disregarded from the contrast. So here are the 6 possible pairwise group differences. If you want to do something other than pairwise, for instance, if I want to know if control is different than treatment period, lumping together all the treatment groups, the last line on the slide would give you that, where I give the control group a -3 because I have 3 groups being lumped together under treatment. It still sums to 0, and then the divisor equals 3, then renders those back into the -1 + 1 pattern. So the p-value that you would get out is the average of it would be control versus the average of the treatments. And you can ask for any kind of combination like that. So if you just want group means and pairwise differences, LS means diff equals all gives that to you. If you want anything more interesting, including group differences and interaction terms, you're going to have to ask for it. For instance, group differences with age. The model line, treatment group, age, treatment group by age. That's all I have to type. Every time I say treatment group, SAS knows that it needs to throw in 3 terms to deal with all differences between the 4 groups. I can no longer say, are the groups different? I have to say, at what age are the groups different? Because group interacts with age. So I have the same idea of LS means group difference equals all of them, but now I'm making it conditional at the centered ages. So the first line gives me group differences specifically among 80-year-olds. The second line gives me group differences among 85-year-olds, which is what I would get on the default output because that's where age is 0. And then the last line gives me age 90. Those numbers are completely arbitrary. I could pick any value of age and get group differences, whichever one you feel like. If you don't specify this at, it will give you group differences at the mean age, the grand mean for the sample. It figures out and gives you conditional differences at that point. Just as we did before, if we have age by group as the interaction of interest, we would want to know whether or not there is an effective age within each group. This is how you do it when group is categorical. Rather than listing the particular age by group interaction contrast that you created, you list the global interaction term here, and then you indicate for which group you want the age slope. The age slope still goes at the beginning because that's the term that you're requesting. So the age slope for the control, age slope for each of the treatments in turn. Last but not least, if I want to know differences in age slopes between groups, I take one group's line and subtract the other. That means the main effects of age cancel. One of these ones flips to be a -1, and you end up with these patterns right here, where you go -1 + 1 for the groups you want to contrast, and zeros again mean ignore that group for right now. How are we doing? Not bad, right? We can do this. So here's where it starts to get confusing. You will see different p-values for the effective group in different sections of the output. The solution for fixed effects may or may not agree with the type 3 tests of fixed effects, and that depends on whether or not it is marginalizing across other variables in the model to create these multivariate wald tests. So for instance, let's say that I have this model right here, where I have treatment group, which is the same as before, and I have gender as a binary variable. If gender is binary, I could put it on the class statement or I could not, right? There's only one difference between the two. It's up to me how I want to do it. The type 3 tests of fixed effects, the multivariate wald tests that are given to you by default, then differ as a function of this decision. So either way, the main effect of sex that's given is the average sex difference averaging across all the groups. It averages across group to give that to you. The interaction is going to be the same either way too. The difference then is what the main effective group means. If gender is treated as a continuous predictor, it's going to give you the omnibus main effective group at gender equals 0, for men in this case. If gender is included on the class statement as well, it is going to average over the genders instead. So it will give you the average effective group for the average person, meaning equally weighting men and women. That, I would argue, is not helpful information, because there's no one in your study who is on average half of both. So one of the things that annoys me about the way that ANOVA is taught is that a lot of this emphasis is on these useless marginal effects. When you have an interaction, the marginal stuff doesn't work. So I want to show you, with just a quick twist of the code, how to get some things that are actually more useful back out. So we have example 2C then in the time that we have left. I'll let you pull that up. Any questions before we dive in? So I have a disclaimer here because I don't care about family-wise error rate. Everything I'm doing is putting all kinds of p-values out there. I believe that 1 in every 20 p-values if alpha is 0.05 is wrong, the end. I don't give any special status to p-values that show up by default versus those that we ask for via estimate statements. I don't. So that's my philosophical point of view. If you are from a world where somebody's going to yell at you about this, on the ls means command, you can ask for some kind of error correction, Tukey, Bonferroni, whatever the hell, there's various kinds. You can ask for your diff equals all to give you corrected p-values if that's something that someone's going to care about. But the way I look at it, like if we have, say, these differences right here for a treatment group, those 3 show up by default. These 3 don't. But if I changed who the reference group was, I'd get a different set of 3 that show up by default and 3 that don't. So I don't view asking for, like, post-hoc test is the dirty word that's applied here. When you ask for more information, it's all of a sudden it's dirty, it's post-hoc. I don't buy that. 1 in every 20 p-values is wrong. To me, it doesn't matter where it came from. So that's my disclaimer. So this is an example from chapter 2. Dementia group, 3-group variable. We're going to look at its interaction with gender. First, doing manual contrasts, then putting one of them on the class statement, and then putting both on the class statement so you can see the difference in the output that you get and what it means. So I am creating dummy codes here. I have none versus future and none versus current. So people who never get dementia versus people who are going to get it at some point during the study versus people who already have it. These groups are not equally sized. The none group has maybe 70% of the sample, I think, if I remember correctly. And the other groups are much smaller. So that will play into our power to detect group differences. I am using proc format to add labels so that when I get the output, I'll know what it means. Note that I am including the original code for the group as well as its label. That way they stay in the same order. Otherwise, it's going to be alphabetical, which means it's going to mess up the order and mess me up when I try to look at the output. So here's my model. We had our age by group interaction from last time. We're going to ignore that for today and just look at these interactions between gender and dementia group. So I have the means summarized for you. It looks like if I do an eyeball test here, there's an interaction. I would say this seems to be the biggest area of difference. The difference between future and current looks to be a lot bigger in women than men. That's just me eyeballing the means. But I'll have to figure out how to confirm or deny the hypothesis. So here's how I would ask for instance, an R-square for the model. I would list out every term that's in the model with a 1 behind it. Here's how I would do an omnibus interaction, where I list out the two interactions of dementia group with gender. Here's how I got those cell means. So if I'm asking for cell means, that means conditional means. This is holding all of the other things in the model at 0 because they're not mentioned. Intercept, and then each other variable that's relevant here, gender, dementia, and the interaction of the two. Then I'm asking for all of the potential simple effects, meaning specific pairwise group differences. So I can get the sex difference in the none group, the sex difference in the future group, and the sex difference in the current group. If you look at the codes here, all of them start with the coefficient for sex and a 1, because at a minimum we need the gender difference, and then how the gender difference differs in the other dementia groups gets a 1 in the second line and the third line. I have included the main effects of dementia with zeros for pedagogical purposes to remind you that they don't contribute to the sex difference. Only the sex by dementia group interaction contributes to the sex difference. I can also do differences among the dementia groups in each gender, and in that case, now the main effect of sex doesn't matter, but the main effect of dementia group does matter. Here are the ones that are none versus the other. None is the reference group. So we have the relevant contrast between none and future here. The interaction term gets a 0 if it's for men. It gets a 1 if it's for women. Likewise, none versus current. We pick up the contrast for none versus current here, and its interaction gets a 0 if it's for men, and a 1 if it's for women. Now the tricky one, future versus current. This is the difference among the non-reference groups. This is an example of asking for the difference in beta weights. So I give the none versus future a -1, the none versus current a 1. The direction of those codes stays consistent when I give them to the interaction term to pick up what it would be for women. Because I already gave dem NF a -1, it has to be a -2. Because I already gave dem NC a 1, it stays 1 here. Two different explanations to try and illustrate that which you think of as the moderator is arbitrary. This one term, sex by dem NF, that you can either think of as how the gender difference differs between none and future, or how the none-future difference depends on sex. It's the same thing, either way. Likewise, same ideas for none versus current. Those two interactions are given to you already by default in the model. The third one is not. If I want to know the difference between the non-reference groups, that's where we go -1, 1. And here is my story. So if I look at just what I would have gotten, this is all I get. Hey, come back. This is the gender difference within the none group. This is the none versus future difference for men. This is the none versus current for men. This is how the gender difference becomes less negative in the future group relative to the none group. And this is how the gender difference becomes more negative in the current group relative to the none group. That's only some of the possible comparisons that I might want to talk about, though. There is way too much text in Chapter 2 going through and recentering everything to show you how the model can be reconfigured to give you all the other missing pieces. That was for pedagogical purposes. We asked for everything we would need to know down here. And I put them in a table. So we have our cell means, whether or not there is a gender difference within each group, whether or not there is a dementia effect within each gender, all possible, all three different comparisons. And then the last part here, the interaction contrasts. So, which way would you like to go? Do you want gender as the moderator or group as the moderator? Gender's the moderator? Sure. So, to what extent does the effect of future dementia differ by gender? No, it doesn't. 1643, if I go back up to my table, is the difference of these differences. So this is like 6 points, and this is 6 points, and those differences differ by, yes. Here's a hybrid. When dementia group is categorical but sex is continuous, this is probably the easiest way to do it, to be honest. In this case, I get group means at particular levels of my covariates. There's the marginals, there's the effects for women, and there's the effects for men. Because group has been put on the class statement, where the dot is different. It's now on the current group. I will point out inconsistencies in the output here. So up here, it looks like there is a main effect of sex, right? Who is it for, though? The current group now. Let's go down here. Here's the main effect of sex, but here's something interesting. The t-value up here is 3. 3 squared is like 9. 3 squared is not 19. So here's a different main effect of gender. Who's that for? It's on average. It's across the average of the groups. So it's not in any one group, it's on average. Here are the group means that would create that average effect of gender. It's literally being held gender at 0.5. Does that bother anyone? Yeah, these marginal things are useless. Here are the the means for means and mean differences. Here's how I would get simple effects of sex for each group, simple effects of group for each sex, and then interaction contrasts, same as before. Last but not least, if we put them both on the class statement, this is where it gets a little tricky. On the one hand, I can get all of the means very easily. On the other hand, I get marginal effects out of everything. Let me introduce you to one new term before we go here, slice. Much, much less typing. I'm asking for the mean for every combination of these two variables. I am asking for all possible pairwise differences with diff equals all. I am doing it by holding the other covariates at values of 0. And slice means per. The word slice means per. So the first one is giving me the effect of gender per dementia group. The second one is giving me the effect of dementia per gender. So all that typing that I did to begin with is contained pretty much in this line, with the exception of the interaction contrasts. And that's where your brain's going to hurt a little bit, because to list out the interaction contrasts, you have to list a value for every unique cell of the interaction of the two variables, which means 6 values. And keeping track of which number is which can be very tricky. To help you, you can add this option at the end of the line before the semicolon, and that prints a table that assigns the 1s and 0s to their respective cells, and you can check to make sure that they're going to the right places. But this is what it would look like to do the interaction contrast, for instance. This first one is asking for the difference between none and future for one gender versus the other. And note the minus are backwards. That comes from subtracting one line from the other. It flips the sign. So, moral of the story. The ANOVA output that you get is marginal is useless. If you have a significant interaction, it will behoove you to try and do these things to try and understand what it means. More specifically, which differences are different. That will give you your story. How you ask for that information just depends on what all is in your model and which way is less annoying. So, ta-da! Now we get to do this in random effects models. Yeah! So it's the end of the cleaning and the beginning of karate after Thanksgiving. So homework due Friday, no class on Monday, no class on Wednesday. Have a great break. Email me if you have questions, and I will see you on the Monday after.